thing relative to where I'm at determine these x, y's, and r values. Now the radius, think of the radius of a circle. Does it ever become negative? No. But if I'm hanging out in a different quadrant, in fact, this point right here happens to rotate along my circle and maybe end up over here, for example, well then now I have a new triangle. And this new triangle has that y value, it has this x value, which is actually negative. And then it has the same r value. The r value never changes, but y and x, depending on where I am at, will become positive or negative. So I'm moving around that circle. All right, so we have this relationship. Now we're going to go. What? You good? So now we're going to go and look at some values here. Sines and cosines. I could be doing this for tangents also. We're going to do sine, tangent, and cosine now. Tangents, cotangents, secants, and cosecants. We're going to worry about those guys later. Those are the secant and the cosecant and the cotangent are known as reciprocal functions. We're going to get to that. So here we are, hanging out with a ray at -5, -3. -5, -3 is in which quadrant? Do we need a review on our quadrants?
Yes.
Okay, good. Quadrant 1. Where's quadrant 1? Top right. Here's quadrant number 1. And then we go counterclockwise, just like we do with our angles. So this is quadrant 2, and this is quadrant 3, and 4. All right. So now back to the question. Where am I if I'm at -5, -3? I'm in the third quadrant. So it's a great idea to do little sketches of this thing. So -5, -3 looks something like that. Here's -5, -3. And again, think about the triangle that you created. We will always generate these triangles where I go back to the x-axis. Don't create these triangles with the y-axis. We'll talk about y later on. Has something to do with what's called a reference angle. Reference angles always come from the x-axis. But anyway, here we are. We've created this angle. We've got this new triangle, and we've turned some angle. We don't know what that angle is, but it would be this. Right? There's our theta that we've spun around and created this terminal ray. That allows us to be at -5, -3. Now, that angle that turns creates this triangle. And then this triangle that has a angle right here at the x-axis. We're just going to give it an alpha symbol. And again, this is a thing we're going to talk about in the future. It's known as a reference angle. All right. So anyway, there's where we're at. It's a right triangle, and that right triangle has coordinates of -5, -3, meaning the y value is -3. The x value is -5. We need r. Well, I could use tangent if I knew what the angle was, but we don't know what the angle is. So how do I find a third side of a right triangle? I know two of them. Pythagoras. There, very good. So we're going to do a squared, b squared, c squared, r squared, or r would equal the square root of -5 squared plus -3 squared, and we get the square root of 34. Don't make a decimal out of it. Leave it as the square root of 34. All right, good deal. We now know that that's the square root of 34. Now, we can answer the question of what is sine? Sine of this angle. Well, sine we know is y over r's. And our y, we just discovered, was -3. And our r, we said, was the square root of 34. Do I leave answers with radicals that have, denominators that have radicals now? No, we want to rationalize those, so we're going to have to multiply everything by square root of 34 in the top bottom. And we get that sine is equal to -3 root 34 all over 34. Now that can't simplify, so we'd be done. So there's our sine relationship. Cosine. Cosine uses the x over r thing. So we have cosine of this theta angle would be equal to x over r, which in this case is a negative 5 over a square root of 34, and we rationalize once again. And we come up with negative 5 root 34 over 34. So there's our sine and cosine values for that point that's in the quadrant number 3. Okay, I want you paying attention as we're doing these problems. I want you to pay attention to the sine, not S-I-N-E, but S-I-G-N. Look at the sine values of these trig functions that we're creating. Right? So pay attention to them. So in quadrant 3, I ended up with a sine value of negative on quadrant 3 and a cosine value that's negative in quadrant 3. Okay? Before we embark on that next one there, questions on what we've done for A? Yes?
How do you know which ones to use?
Okay, when you say which ones, what do you mean which ones?
Cosine, and tangent.
How do I know which ones to use? Okay, first of all, this problem asks me to identify sine and cosine. It's telling me what to do, right? So, does that answer your question? Any other ones? No? Okay, try B. Okay, so first, negative 4, 7 is in quadrant 2. Right there. There's negative 4, 7. Here's the triangle that we create. 7, negative 4, and my r value. The angle that got me there, theta, creates a reference angle of alpha right there. So there's my triangle that results. Then we got to go find r. We do that by doing our square root of negative 4 squared and 7 squared. Then we go find sine. Again, sine is measuring y over r. So sine of this theta angle would be 7 over the square root of 65, which becomes 7 root 65 over 65. Cosine measures x of the triangle. Negative 4 over root 65. Negative 4 root 65 over 65. How do you guys do? Get it? All right. So again, paying attention to the SIGN sine values of these. Notice that these guys, look at the sine value in this example was positive, where over here, under example A, was negative. The cosine value of B was negative, as it was in A. All right? Yes, Miss Brooke? There is. How do you think you can do that? And what is it? But in this class, we don't use the acronym of all students take calculus. We use all support the covers. Yes. But yes, you're absolutely right. There is a way to tell what sines and cosines and tangents are going to be in each quadrant. We're going to get to that in just a second. Fourth quarter. No, not fourth quarter. What am I thinking? Fourth quadrant. Got some angle hanging out in the fourth quadrant. It produces a sine ratio of negative 5/13. What's the cosine ratio? Again, I'm always a big proponent of sketching. What do we have? So I'm in quadrant number 4. So I'm down here somewhere. There's my r value. And in quadrant number 4, the triangle that I create would look something like this. There's the y part. And here is the x part. There's my triangle. The angle that got me all the way to that point, theta, would look like that. And then once again, here's the reference angle that we're talking about. Well, we're mentioning, but we haven't done anything with it yet. So there's my sketch. And it told me that the sine of this angle theta was equal to a negative 5 over 13. And that means I know what my y and my r are. Because I know sine is y over r. So I can plug those things in over here. So this is a 13. This is a negative 5. I need to find out what x is. So again, we're using diagrams. Yes, ma'am?
Can you tell if it's going to be negative or positive by whether the x and y is negative or positive?
Exactly. That's what Brooke was saying. Yes, you can. There is a way, we will know in just a second, that I will know automatically whether it's positive or negative, just by where it's at. So, if I want to find x, now, can you tell what it is? Is it positive or negative? Is this x positive or negative? It's positive because it's going to the right of the origin. So I know that the x value needs to be positive, which by cosine means going to also be positive. So first we've got to find x though. And you find x by doing the square root of 13 squared minus 5 squared. Or the square root of 144, which is 12. This is called a perfect triple here. 12, 5, and 13. Well, x equals 12. All right, and therefore, you know this is the cosine of that angle, which is an x over an r, is equal to a 12 over 13. So it's a positive value. All right. Any questions on that one? Pretty simple, huh? All right, let's give you guys your shot at this one then. Quadrant 3. There we are. Angle that took me there. Reference angle that resulted. And then negative 3 and 5. There's your 5 for your r. Negative 3 for your x. 5 squared minus 9. 25 minus 9 is 16. Square root of 16 is a 4. And it's going to be negative because it's going down. So my sine value for this should be negative 4/5. All right, so we paid attention to all the values of sine being positive, negative, cosine being positive or negative. There is a way to know where they hang out. So this circle that we were initially looking at, where my radius could be anything, now we're going to look at it with the specific radius of 1. This is called the unit circle because radius equals 1. And you'll see that in the unit circle where the radius equals 1, notice how your sine and your cosine ratios change. X over 1, y over 1. So now you're just expressing y's and x's for sines and cosines. Sine is a measurement of the ratio of the y values to the radius, but the radius went to 1, so now we're just saying sine is equal to y and cosine is equal to x. All right, now, the domain and the range of these guys. So what's the control variable here for these unit circles? R. Is it R? What do I mean by what the control variable is? So when we calculate y equals sine theta or x equal cosine theta, let's just stick with the y one for a second. In this equation, what is the dependent variable and what is the control variable? y is the dependent, and theta is my control. So theta is my angle that I turn. That's my rotation. Is there any limit on how I can turn an angle? Can I go positive? Can I go negative? So it can be anything, can it? So if I have this answer here for this, theta being equal to my dependent variable, and over here in the cosine world, I've got x is equal to cosine of theta. There it is again. There's your your control variable, and this time x is actually my dependent variable for cosine. But for both of those, for sine and for cosine, my theta is what determines my domain. And so if theta can be positive, negative, 0, it can be anything. That means in the sine and cosine world that we're going to be working with here, that means theta is allowed to be all reals. That would be the domain of these functions. We haven't graphed them yet, but when we do graph them, you're going to see that they just keep going on in both directions. Unless we just restrict our domain. But yeah, theta equals all reals for these things. Now, if you were just looking at the circle part of this, and you thought, okay, x part of the triangle, y part of the triangle, there's my x, which is domain, there's the y, which is the range, then this would be a different answer. The x part of the circle would always go between -1 and 1. Gets smallest at -1, gets biggest at 1. And the same thing happens with the y's. Gets biggest at 1, gets smallest at -1. But we're not talking about that. We're actually talking about this relationship of theta to either the y values or the x values at this point as it spins around. So that's why in this example here, the domain, we're limiting it to just the theta. Now in terms of the r's, so thinking about the fact that theta can be anything in both of those y equals sine theta, x equals cosine theta equations. If I put anything in there, from 0 to 360 or 0 to -360, doesn't matter. Since it's a circle, I'm going to get repeated y values all the time. And if I were to look at y being equal to sine, and take a look at my unit circle, the largest y value, smallest y value that I can have is -1 and positive. So the domain and the range of a sine function, since sine measures y, is going to have to go between -1 and positive 1. So, what about the cosine function? All right. Well, the cosine function goes from a -1, 0 value to a +1, 0 value, because then it measures x. And so it also has a range of -1 to +1. So they both have the same range, but they both have the same domains. And when we graph these things, you're going to see they're called periodic functions because they repeat their pattern. They're a bunch of wave-looking things. All right. Here's a little visual for what we're going to be talking about next. Has anyone paid attention to the fact that there are going to be some spots as I spin around this circle? There are some locations where there are no triangles. Has anyone even thought about that? Yeah, there are 4 places where no triangles exist. So let's see what happens on those. Where did it go? No. Where is it? Ah, there we go. All right, so here we have, is that big enough? That's better. So watch what happens here. You see your triangle, there's your triangle, and then you have your angle 60 degrees in this yellow-green looking number. Here are your x values in the bottom. So I'm in quadrant 1, obviously. But there are 4 places. You guys can probably already guess where it happens. Right there. Pretty darn close. So on 90 degrees, my triangle disappears. Well, which part of the triangle actually disappeared? The x part of the triangle disappeared. So x became 0 at 90 degrees. Okay, keep that in mind. So x became 0 there. Well, we kept going. Oh, there's my triangle again. There it is, there it is, there it is, there it is. Oh, uh-oh. It disappears again. So it's disappearing on the axes, right? Positive, the negative axis. So look what happens. What happened on that is the y part went bye-bye. The x part became the same thing as, uh-oh. What does it become the same as? Watch the x part. It becomes the same thing as which part of the triangle? The r. It becomes the same thing as the r. So that's what happens. Is my y's and r's become the same thing when I'm on? Come on. When I'm on an axis.
Get out of here.
Get out of here. Yeah, well, we're not going to keep going. But you can see that there are those four places where my triangle disappears. Those are called quadrantals. And so we're going to get to that in just a second. Keep the idea of x is disappearing, y is disappearing on the axes. So what are the values of sine and cosine and tangent in each of these quadrants? So now we get finally to what Brooke was telling us. And Brooke has already told us that. That both sine, not both, that these three functions are all positive in quadrant 1. They're all positive. And why are they all positive? Because in this quadrant, if you have a coordinate, the x is positive and the y is positive. So if cosine measures x, it's going to be positive. If sine measures y, it's going to be positive. If tangent measures y over x, it's going to be positive. So what we say is that all are positive in this quadrant. And then we keep going, and we go over to quadrant 2, and we recognize that in quadrant 2, the only one that is positive is a sine. And that is because, look at this, it's amazing. In this quadrant, x's are negative, y's are positive. So if x's are negative, that means cosines have to be negative, which means tangents have to be negative. So we have just sine. And so we say all, and then support for sine. You gotta get it. You get it. And then down quadrant 3, what happens is tangent becomes the only thing that's positive. Tangent is the only positive, and that's because both x and y are negative. It does. So there's our acronym for the. All support the. And then finally in quadrant 4, the only thing that's positive here is cosine. And that is because x's are positive, y's are negative. And so the covers all support the covers. A, S, T, C. That's how you're going to remember what the values of the functions are within each quadrant. That just means the positives. And so cosine is going to be negative in quadrants 2 and 3. And tangent will be negative in quadrants 2 and 4. And sine will be negative in quadrants 3 and 4. So there we go. There's the ASTC acronym. We're almost there, folks. Hang in there. So what are the SIGN sine values of these angles here? So this is a good review, actually, from a couple days ago. Radians and degrees. You got to think about how does this convert to degrees. So negative 2 pi over 3 is my rotation. So does everybody remember what the divide by 3 radian was in terms of an equivalent angle? 60s, yeah. If I divide by 3s, I have 60 degrees. So I have 2 of them, actually. 2/3 or 2 60-degree angles means this is the same thing as negative 120 degrees. So think about where you're at. What quadrant? 3. I'm in quadrant 3. What is sine going to be there? Good. So sine is going to be negative in quadrant 3. And what is cosine going to be in quadrant 3? It's also going to be negative, because the only thing that's down there that's positive is the. 3 pi put us?
On the line.
Which line? The x-axis, but which axis? What one? It's the negative x-axis. Look at it, watch. 2 pi, 3 pi. 3 pi. Puts you on the negative x-axis. And then thinking about what happens on the x-axis. So I asked you to hang on to your thoughts about what things disappear on the axis. Here's where I want you to relive those moments. So what disappeared on the x-axis? What became 0? Your y's did. So if my y's had become 0 and sine measures y, what's the value on the x-axis for sine? 0. Right? Now, think about x's. Cosine measure x. Y's disappeared. X is specifically which value right now? What is it over there? It's negative 1. Now, I didn't ask us for the actual numbers, I just wanted plus or minus. But that would be your value for the sine and cosine of that. And then we just keep working our way around. 72 degrees, where am I? That's all of them. So sine of theta would be positive. And cosine of theta would be positive. 315. The cosine's positive because I'm in quadrant number 4. So that ASTC thing is like an important understand. You need to understand what that is. It helps you very easily determine your value. And then last of all, any questions on that? Sorry, guys, I'm just kind of flying here. Any questions on that? And then lastly, before I think we're almost done. Yep. Okay. So going back to the quadrantals, you guys are gonna help me. Actually, you're gonna help me rattle these off real quick. Thinking about what disappears at these angles. Does x disappear or does y disappear? Will help you answer the questions for this thing. So why are they called quadrantal angles? They're at every 90. There are 4 90s and a 360. That's quadrantal angles. Think about it, 90 degrees. Here I am hanging out at 90 degrees. What's sine? Is it 0? Is the value of y right there equal to 0? Oh, it's 1, yeah. So the sine of 90 is 1. All right, how about cosine?
0.
Because they disappeared. X's disappear on the y-axis. All right? Now here's the one that maybe you're not so familiar with. So tangent is equal to a y over an x. And one of those disappeared. Which one disappeared? Yeah, this becomes 1 over 0. So that means tangent is going to be undefined. Right there. Okay, let's keep going. Sine of 180. So now I'm hanging out right there. What is gone? Zippo. Y is gone zippo. So that means sine of 180 must be 0. No, not 1. Negative 1. So remember, positive 1 is on the positive x-axis. We're on the negative side of the x-axis right now. So cosine is negative 1. And then tangent. Y over x. 0. 0 over a negative 1, right? 0 over negative 1 means 0. Okay, now here's the easy part. Once you know those, the other ones kind of follow suit. So back onto a vertical axis now at 270. So now I'm hanging out down there. Negative 1 now, come down on the bottom. 0 and, just as it was above, undefined again. So the tangents kind of don't exist at all on the vertical axis. And then they become zeros on the horizontal axis. So over there I'm going to get 0, 1, 0. And voila. Okay. Last little FYI piece of information here. So tangents, cosines, and sines sines repeat their values every 360 or 2 pi rotations. I get back to the same place every time. And if that happens, then we can express these trig functions as a relationship between some initial angle plus k times pi, or k times 360, k being an integer. What do I mean by, that's supposed to be an integer. What do I mean by that? So if I went around 1 time, my k would be 1. If I went around twice, my k would be 2. 4 times, my k is going to be 4. So 1 times 360, 4 times 360, 2 times 360. Generically speaking, this could be written like this. Plus k times 360 and theta plus k to pi. I can write it like that as well. But it just basically means if I repeat, if I cycle, I always get back to the same value of that sine or that cosine. That's all it does. I think you have a little, I think there might be a homework problem or something that talks about that. So there it is. Okay, well, how do we do? Any questions before we disengage?